Yeah, okay. Today we have our fifth laboratory work, and we are going to work with band structure of 2D crystals. In laboratory 2, we not 2 but 3. In laboratory 3, we have talked about just common band structure for 3D materials, for bulk materials, and in 4 laboratory we have used relaxation. And now we will combine all the things for band structure, of 2D crystals. And I am gonna give you some theory, some repeating, and some things. Oof. Yeah. So what about band structure? I don't know if you have read this book. Sorry, the surfaces. Because I used it mostly for this part of lecture, and Roald Hoffman in 2 weeks will be in Ukraine, so we'll have announce of his lecture. Okay, what's the story? We have this chain of atoms. It's the most simple chain. We have chain of atoms with wave functions. He 0, he 1, he 2, and so on. Distance between these atoms a. Atoms are going from 0 to infinite, and we have we want to combine these orbitals. So we want to create some general orbital for this chain, and we can do it with just simple sum. So we can use this he n multiply on exponenta ikn a, and we have general psi function for this chain. And what's for each atom 0, 1, 2, and so on, we have very localized electrons. We say, for example, it can be some kind of hydrogen. We say that all this electronic density should be located somewhere near the atom. And when we go to the next atom, this atom almost not fill this atom, just only this intersection. So they have very small intersections. Mostly they are independent. They are localized near the atoms, and we can make this simple sum of this psi functions. Then we can divide it into 2 parts for key for wave vector equals 0, and wave vector equals p divided by a. So it's the center of brilliant zone and border of brilliant zone. And for key equals 0, we have just sum. We will say that this orbital will be bonding, this will be anti-bonding. So if we have just bonded orbitals, we have the lowest energy. If we have some combination of bonding and anti-bonding, so in some excited orbitals, we have lower energy than in this case. So we think that this is the lowest energy, this is not so low energy, this is higher energy. And then we plot some dispersion. The most simple, the most common dispersion is just linear dispersion. It means that impulse of our particle will be h multiplied by k, just h by k. Then we can calculate kinetic energy of this particle, and we get this parabola. So we have this anti-bonding. We have this bonding. It will be bonding, so it should be all filled with color. So we have this bonding state in the center of brilliant zone, and we have this anti-bonding states in the borders. Low energy, higher energy, and it's very simple representation. But what should we do for more compact systems? For example, for a surface. And today we will work with graphene. Graphene is 2D crystal, so this surface things is very important for you. We have such crystal structure, very simple, very common. There's one atom, second atom, third atom, and so on. We have this. It's like infinite chain of atoms, then another infinite chain of atoms, and so on. We have some coordinate systems like x, y, vector a1, vector a2, and we want to create Brilliant zone of this surface. It's rather simple, and Brilliant zone of this square will be also square. Because what is Brilliant zone? It's like I take 2p divided by first vector, vector a1, and I'll get some b1 vector. Then I take 2p divided by a2, and I get some b2 vector. And I have this vector, this vector, and if I have square lattice, I will have square Brilliant zone. If I have not square but rectangle, for example, A more than B. In reciprocal space, this side will be shorter. So because 2p divided by A, it will be shorter than 2p divided by B. B is lower than A. So this square lattice will go to square Brilliant zone, but rectangular lattice will go to also rectangular Brilliant zone, but moved. So because for longer side, you have shorter side. That's why when we used this automatic key points in our calculations, that's why we usually use for longer lattice vectors, we use less number of key points than for shorter, because longer lattice constant will create shorter side in Brilliant zone. That's why here we need a lower amount of key points than here to make the equal distance between these key points, to make this equal mesh. Okay, what about special points? We also have worked with special points. Maybe when I talked about them first time, it was not so clear, but I hope now it's more clear, because now we have worked with all these points. Gamma point 0, 0 is the center of Brilliant zone. And then we have some special point, for example, x. X is the center of side of our Brilliant zone. X, p, what will be its coordinates? P equals p divided by a here, and 0. So 1, x, and the same point we'll have here. By x, it will be 0. By y, it will be p divided by a. So we have the same point, but with two different coordinates. And for example, we have m. M is the corner point. We have m here, 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 and here. 4 points. So it's special points in the very, very simple and very basic surface. And let's work with some, let's fill it with these atomic orbitals and create some band structure of this simple surface. If I will fill these points, that if I will fill that lattice with our orbitals, I will get in gamma point the lowest energy, and I will have all bonding states. So it will be the lowest point, gamma. Then for these border points, x and x, for chain of atoms, it was like bonding, then anti-bonding, then bonding, then anti-bonding. And I will combine it. As I told, we can see it like chain of atoms, another chain of atoms. So it will be the same. For example, here will be one chain of atoms where we have bonding, anti-bonding, then bonding, anti-bonding. And the same chain of atoms will be here. It will be, what will be this point? It will be M point here. No, it's X point, X point. So this can be X point. And then we can move them. We can use the same, we can take this chain with bonding, anti-bonding and move it. Here will be anti-bonding, here will be bonding. And we have, when we have another point. Then we have another point because we can locate this chain of atoms here, bonding, antibonding, bonding, and so on. So we have all these different combinations for corner points. This will be for x point, and this will be for m point. This combination in the border of our Brillouin zone. And we know that this is the lowest energy. Then we know that this energy is higher because this bonding and antibodies are mixed in some way, and this energy will be even higher than this and this, because here we have at least one chain of atoms with bonding. Here we have antibodies. It's almost also rather low energy, but here we have totally mixture. Not random, but is a mixture. We can say that in this direction we have all bonding states, for example. That's why m point will have higher energy. And if I will use this parabolas for this Brillouin zone, I will say that gamma will be the bottom of this parameter, center of the parabola, center of this parabola, the lowest energy. Then I go to the edge to x. It will be higher energy. We have higher energy. Then from x, I go to m. It will have even higher energy, and then I will go to gamma. So higher energy, and then I move. I place this parabola from m to gamma, and I have this very simple band structure. And you saw in our calculations that we also use this closed circles. So we have gamma, x, m, gamma. Because in this way we can include as much, so we can include all these points, and we can see all interesting things in this path. Here will be our path. And it's a rather common path for 2D crystals. For graphene, it will be, I think it will be the same. Gamma, x, m, gamma, yeah, it will be the same for graphene. It's band structure of the surface. I hope it's clear how we can build it. And you see, we didn't use any hard mathematics. We just took this parabolas with very simple dispersion and just filled all space with these parabolas, and we get something. So we get something reasonable for our simple system. Okay, we have worked with s orbitals, these circles. We have told that we have some analogous of hydrogen atoms. We have this s circle orbitals, and if we will make the system more complex and include p orbitals will be like this eights. So it will be slightly harder than just for s orbitals, because for s orbitals we could make only we had only two possibilities: bonding and antibonding states. Here the situation is not the same in different directions. In this direction, we have this bonding with antibonding. In this direction, we have another bonding. We have this bonding part with this bonding part, and this antibonding part with this antibonding part. So they're not symmetrized. In gamma point, what we will have in gamma point, we'll have so this is the lowest possible energy configuration for p orbitals. When we can place them in this way, it's the lowest energy. It's the lowest possibility. This way or this way, it's the same. It's the same. If I will just move it, x and py. For x, for point x, you have this situation when here will be bonding. Again, bonding will be this situation. Of course, what is x? What is sigma bonding? I think you have heard about it, about the sigma bonds. Sigma bonds is the most sigma bonds is the hardest bonds. Where it will be? It will be here, in this part. So because here we have these orbitals as too close to each other. So you have hard bond here, hard bonding here, and p bonding. P bonding is very is not so strong, and we have p bonding here in this direction. So it's like sigma and p bonding.
What's the difference between sigma star and
sigma star? Sigma means that we have here bonding and bonding, and sigma star means that we have some mixture. It's like sigma bonding, it's sigma anti-bonding. Because here we have these combinations. This combination is also okay, but this is some mixture. So this bonding will be lower than this bond. What else should I say? Yeah. Oh, we have this combination for gamma, for x, for m, for y. Now we take y is the same as x, but we should change them in some way. So in this in case when we include these p orbitals, x in this side and x in this side, they will not be equal. That's why we should change. We should change the name. So we should separate them in some way. And what's the story? The story will be much more complex. We have y will be here. So in this case, this orbital and this orbital, they are not exactly the same. Y and x orbitals. You see that they are not exactly the same. So we have this gamma x m gamma for s orbitals, which I showed you on previous slides. This is our lowest energy orbitals. Then we have higher energy orbitals, and it will be slightly harder to understand what is going on. So here will be gamma point, gamma. Then we are going to x point because of this sigma bonding, because this thing, it will be slightly lower in energy than this than gamma. Then we go into m point. What is m point? Here. M point, and we go into gamma. Gamma. We have one. So, we have one bond. We have another bond, this bond. And we have, it's for px, py bond. And we have pz also. We have pz. Pz will be located like this into the screen. And for pz, we have this gamma when it's the same but in other direction. Pz. Then we are going to some x. X, it shows that x will have lower. It will have higher energy than gamma. So this thing, but inside it will have high energy. In M we have even higher energy, and then we back to this pz thing. So we'll have another bond. In this px and py, they're almost the same in this representation. Px and py, we just turn them. Pz will be different from them, and that's why we have two bonds. They are called degenerated bonds, because for px bond and for py bond you have the same bond, and here in reality here we have two bonds, but they are the same. So they are the same. They are called degenerated. 1, 2, 3, 4 bonds. Each bond, each band for each orbital. S and 3p. And the thing is slightly more complicated. It's just a picture of brilliant zone of crystal. For 3D crystal, we have much more complex situation, and I will not consider it. But you can go to Hoffman book and you will see this beautiful pictures with this lot bands with a lot of these orbitals, all these combinations. It's rather crazy. Okay, what about graphene? And I also want to show you some interesting stuff about graphene. I want to calculate dispersion of graphene. Dispersion means dependence of energy to wave vector. Okay. For very simple situation, for very simple case which we have considered now, we used just parabola dispersion, quadratic dispersion. It's very simple. For graphene, we should calculate dispersion of two atoms A and B. I hope you remember that for graphite, we had 4 atoms in unit cell. Yeah, 4 atoms. Graphene is just one layer of graphite, and we can create it from only 2 atoms. We can have only these 2 atoms, A, B. They are the same, but I name them A and B, and in these periodic colors to change them in some way. Because in our calculations they will behave differently. And I can apply the symmetry operations and create all this stuff, all this hexagonal lattice for graphene. I have cell vectors A1, A2 here. They are. I have distance between these atoms. I start here from this B yellow atom, and to A I have vector delta 1, delta 2 for A here, and delta 3 to A here. I don't have any other neighbor atoms. I have, for each atom, I have only 3 neighbors, and I should work with them. And what's the idea? It's called tight binding model. I don't know, have you heard before about this tight binding model? The idea almost the same as I just told you. We have these localized orbitals in some atoms. So we think that electrons are localized near the atoms, and these atoms, they have very slight intersection of this of electronic densities. So they are almost independent. And that's why it's called tight binding, because electrons, they're tightly bond to this atom. This atom to this atom to this atom, and so on. And I want to create energy to calculate the whole function, the whole energy, and so on. From this crystal structure, I can build this Brillouin zone. For square lattice, it was square. For hexagonal, it will be hexagonal but rotated. It also will be hexagonal, this Brillouin zone, with all these points. Gamma point in the center, key point in the corner, M in the center of this side, and what else? And B vectors, B1, B2. B1 is like 2p divided by 8.1, B2 is like 2p divided by 8.1. And I have some coordinates in this vector basis. What's the distance between each atom is A. Just A. Just A is the distance between A and B. Then I say that this is center of my coordinates, and I can create this vector. For example, to vector A. If this is X, then Y. What will be this A? It will be like it's cosine. It will be like cosine of 16 and sinus of 16. If I'm if minus, because we have this this is X, and we just reversed it, and this goes to another part. So it goes to another part, another side of X, and we should to reverse this one, and it will be 0. So that's why we can use we can move this minus here, because nothing will change if you apply minus to 0. Yeah. And now we have a lot of some mathematics, not very hard. It's rather simple mathematics, but we should work with it. Okay, type Beigen model. The same picture as I showed you a few slides before. Localized electrons near atoms, they are slightly interlapped or connected with each other, but almost independent. What will be Schrödinger equation, stationary Schrödinger equation for this or some n orbital, this H Hamiltonian on Psi and K, and we can calculate this energy for each atom. Then we can apply our border condition. So we can say that if we will have translation on R, so we can move from here to here, we should get the same. So this thing should be this thing. And we can make, as I told that if they are almost independent, we can we can apply this border conditions. We can apply this Bloch conditions to calculate this general psi function, which will be just sum of these psi functions. So this will be some one atom psi function, and it will be a general psi function. And from it, we had to get, in some way, the energy. In time-period model, Hamiltonian will be looked like this. It's just also rather simple view of Hamiltonian. It's creation and annihilation operators, creation with this cross and annihilation, and for B. This is for atom A, and this is for atom B, because we have two atoms in our cell. And we just, I just will make, we have sum of them, creation and annihilation. So it so one particle created here, it moves here, or it don't move here, but it stays here, or it moves here. So we should consider all this variance in this Hamiltonian, EG. So we should create all these things. And T is Hopper integral. So it's some Hopper integral shows some probability that particle created here will move here to this Hopper integral. We think that they are the same because we have same atoms, so it will be the same for A to go to B as the same as A go to as B go to A. Type being Hamiltonian. Very simple. I hope. What we are doing next? Then we want to. Before I worked with A and B atoms as different atoms from some different sublattices. But I don't want this G parameter because it's just another parameter. I want to cancel the G parameter in some way. How can I do it? I can say that G is E plus delta, because I have these deltas, these vectors between atoms, So this is E atom, this is G atom, and I can say that, okay, this G is the same as E plus delta something. It's like 1 plus delta 1, 2 plus delta 2, and so on. And I will make this simple thing. G is like E plus delta. Then I will go to reciprocal space, and I had to have some expression for these operators in reciprocal space. It's also rather simple. It's just this transformation. This is creation operator in reciprocal space in Brilliant zone, and this is our creation operator in real space. And we have just this additional sum of exponents. Then I substituted to Hamiltonian. I have the same for B. I substitute O in Hamiltonian, so it's really not hard mathematics. So we can one just should carefully substitute all these operators inside Hamiltonian, and we'll get something, some multiply of these exponents, and then we have these operators, but in reciprocal space. So we moved. So here we moved from a real space Hamiltonian to reciprocal space Hamiltonian. In reciprocal space, it looks slightly ugly, but it's not a problem. HC is complex conjugated, the same thing, but complex conjugate. Okay, then we say this is delta function. It's not like delta, like distance. It's like delta function. This exponent, we can that's why we can cancel this exponent. It became slightly more convenient without that exponent. Yeah, and here I applied this complex conjugated thing. So this is Hamiltonian. This is Hamiltonian for real space, and this is Hamiltonian for reciprocal space. And I should work here. It's a common idea how we can go from real space to reciprocal space. So we had to make some transformation of these operators. This transformation. Then we should substitute it one by one. So substitute this transformation for B. It will be, if I said that it's like E plus delta, so it will be like the same as so it will be here. It will be K plus delta or minus delta in this space. We will substitute it carefully here, and then we have this Hamiltonian. It looks like almost the same, except the sum. Here, the sum was only for each atom, Eg, it's the number of atoms. And here is like also for each atom, but in reciprocal space, K, for vectors. We have these operators. And we are almost, we have almost done the drop. We have this Hamiltonian. Then I take very general form of Hamiltonian. So it's like psi complex conjugated on some small Hamiltonian on psi complex conjugated. I say that I can show this multiplication as some multiplication of some matrix psi and psi complex conjugated. So if I will multiply them, I will get the same thing because it's some matrix. And that's why I have, and I can say that in very general form, this small Hamiltonian in our Brilliant zone will look like this: some delta K and delta complex conjugated. if I will place this delta k, it's just name of this exponent. So if I will place it here, then I will make all the space matrix. So I will multiply this on this on this. I'll get something like this. So it's the energy. It's the energy of this system of two atoms, and this is what we have looked for. This energy. But this deltas, delta k, delta k complex conjugated, they are rather ugly. So it's rather hard to deal with them. So we had, so it is general, it's general form. And now we are returning to our coordinates. And now I will just place all these coordinates in these deltas, and I will calculate them. So what is so we have sum of three exponents for delta 1, for delta 2, and for delta 3, because we have these three connections. And it will look like this. It's very simple. Delta 1, delta 2, delta 3. Connections between atoms A and B. And then I just place this these coordinates. So it will be some mathematics. I move this exponent to here. Okay, you can just after the lecture you can take this presentation, maybe make it by yourself. So it's really not so hard. So you take this exponent here. Here will be some minuses. 1 minus 3, 2 minus 3. Then I place delta 1, delta 2, delta 3. And I will have this A, this distance between atoms A and B. I will have them, A. What is K? K, both K is vector, but here I have some parts of this vector, Kx and Ky. I have made it. So K both is like Kx plus Ky multiplied by E. And I have this thing. What is cosinus of this thing? It's like exponent with this thing multiplied by I plus the same exponent but multiplied by minus I divided by 2. Then I divided by 2, multiply by 2, and I get this cosinus. So I have created, then I also have to make some simple math to get this thing. So from this to this, what should I do? I should multiply if energy is like root square from this delta k and delta k prime, delta k complex conjugated, this exponent will go on. I have to multiply this sum on the same sum but complex conjugated, but with minus I, and I'll get this formula. This formula, this is energy dispersion for graphene in this tight binding model. If I will substitute, okay, we get the formula, and I want to see what this formula will look like in this interesting columns, in this columns, K and K prime, in this columns. This. What had I do? I had shift all this mathematics to these vectors, to this and to this vector. And I'll get what I will get from here. So what I wanted to get? I wanted to get some velocity of electron. And they are here, this velocity. 3AT divided by 2. T is Hopper integral. A is distance between A and B. and 3 divided by 2. So this is how we moved to this point. I wanted to see what will happen in this point. In this point, the dispersion will be another. You will have this velocity. I just say that this is. I just say that this thing will be Fermi velocity. This and it will be huge. It will be very huge for graphene.
Up to 10 to the 6.
10 to the 6, yeah. It's very huge.
Can I ask a question?
Mm-hmm.
At some point, we stated that we can substitute those exponentials, like exponential I, K, something by delta function.
You mean maybe here, yeah?
No, by actual delta function, Dirac delta function.
Dirac delta function. You mean this, yeah? Because you see, it's what will happen if k and chi prime is the same vectors, k and chi prime. So these vectors are very close. They're so close that we can say that they are almost the same. When they are the same, we have delta function from the thing.
But when we are not the same, we have 0. Why is it?
Yeah, we have 0.
Why is it?
Because we told because this is our time binding model thing.
Okay.
It was our assumption that inside item we have 1 and outside item we have 0. So it goes from our assumption. And this model, even with such assumptions, it works quite well. So we can create this formula for this Hamiltonian. It will be like Vf, this Fermi velocity, on some very small vector q, and on sigma. What is sigma? Sigma is just this Dirac matrices. Pauli matrix, yeah. And we have this formula, and it means linear. Dispersion. And I have used such program. It calls Grapher in a MacBook. I just typed all that formula. I hope you see it. I just typed that formula here as just mathematic formula, and I get such beautiful thing. So this is you see, it's really beautiful. It's like hexagonal. We clearly see this hexagonal thing. So it's reciprocal space. This is the energy in reciprocal space, and we have this Dirac coins. I think it's really beautiful. So from this time binding model, we got very beautiful mathematics thing. You see the algorithm. First we have relaxation, and we will from relaxation we'll get the structure. We'll get the more or less good crystal structure of our graphene. Then as in previous laboratories, some consistent calculations, then band structure, some post processing, and graphs. So, but we will have some. What will be the differences between graphene and graphite? So last time we used graphite. Here's it to the right, graphite input file and graphene input file. Difference not so huge, but rather crucial. Okay, this prefix is not important. what is important? So you see here, I type CLDM1. It means that A and B vectors are the same for graphite and for graphene. But what is CLDM3? CLDM3 is a ratio of C, of vector C, divided by A. And here it was like 3.15, then it goes to 2.70 something after relaxation. But for graphene, I typed 10. So for graphene, vector C 10 times bigger than CLDM1, than vector A. So it's like if CLDM1 is 4.6 Bohrs, so vector C for graphene will be like 46 Bohrs. It's almost 23 angstroms. It's huge. It's very huge. It's really very huge. And why I do it? I do it because I had to use these border conditions in because graphene is some bulk material, and it translates to in all directions, A, B, C directions. Graphene is 2D direction, is 2D crystal. So it translates only in A and B direction, but in C direction, the translation is broken. And I will show you how it looks like in the machine. Now I want to use Materials Cloud SIG-Pass to show you the difference between graphene and graphite. Here is SIG-Pass. Here I will choose my, firstly, I will choose my graphite file. Here is here's graphite as we saw it last week. So you see a lot of this layers. This is unit cell. In unit cell we have 1 and 2 layers, and then we translate them, and this layer goes here, this layer goes here, and we have this brilliant zone, this beautiful hexagonal brilliant zone. But for 2D crystal, brilliant zone, how it should look like? What? Yeah, it will be flat. It will be the same. It will have the same hexagonal form, but it will be flat. And this is bulk, so we don't need it. How do you think if I will take this cell and I will make it 10 times bigger, what will happen to this direction, to this? Yeah, it will shrink and it will be 10 times smaller. So to make flat, or okay, we can't make ideally flat a brilliant zone, but we can make almost flat a brilliant zone. We should have very, very huge lattice in C direction. In this direction, C, you should have very huge lattice. That's why here you see it was like 3.15, and here I took 10. If I will take 20, it will be 20 times smaller. But 10 is okay. 10 is usually okay. Yeah. Because we will have a bigger unit cell. And now I will show you this my graphite, my graphene file from the calculations that I had done. This SF. And here is graphite. You see how it changed. Yeah, we have only this layer, very, very huge cell. So this is like vacuum layer. And then we have our translation. We can't avoid it, because density functional theory is based on this Bloch border conditions, and we had to satisfy those conditions. That's why we can make calculation like this. So we should apply some huge, it's like some vacuum layer, and we think, okay, maybe this baryon zone will be not ideally flat, but it will be closer to flat. You see how it changed comparing to graphite. Here's graphite here, and here is our structure. Here is our graphite, and this is the common thing for all 2D crystals. If you are working with 2D crystal, you should make 2D in some way, and usually we make it with adding this vacuum layer. It will be like 20 angstroms of vacuum layer, and usually it's enough to change any interactions between this and this layers. And this thing is rather thin. Okay, what another difference we have? This one difference, and another difference are coordinates. You see here we have for graphite, we have 4 coordinates for these two layers. But for graphene, I just left one coordinate, one layer. You see 0.25, 0.75. It's in that direction. In that direction, what we have, so this is 0.25, 0.75. I need something in the center. It's not necessary to have something in the center, but I think it will rather okay if it will be in the center. It can be not in the center. It can be in the this corner, but I will add here vacuum layer. I made it in the center just for symmetry, and I just left one layer 0, 0, and then 1/3, 2/3, and 0.5. So I shifted this layer to the center. 0.5 means that it's in the center of the unit cell, and that's all. So that's very simple thing. This very simple methodology how I created graphene from graphite. I just took 2 coordinates, not 4 coordinates. This is, for example, will be A atom. This will be B atom in like it was in our calculations previous for tight binding model. A atom, B atom. So we had to have only 2 atoms. I removed all other things and just I made this 0.5. It means it's in the center. Also interesting thing, it's eyebrow pseudo free. So this is relaxation stuff for cell. How we will relax our A, B, and C vectors. And if I say type eyebrow pseudo free, it means that it will relax A and B and C vectors, but it will left it inside this symmetry. So it will not change symmetry, but it will not change A, B, and C vectors. But if I use 2D XY, it means that I can change only X and Y, and I can change that. I can change that huge that direction. How do you think if I will allow all parameters to change, what will happen? Yeah. If we'll have a lot of calculation time, so we'll have a lot of iterations, but then it will go. This will go to that's why we shouldn't change it. We shouldn't change this lever, so we should fix it, and we fix it with this command 2dxy. I can show you it in here. Cell do free. Here is cell do free, and we have a lot of possibilities. Eyebrow, it means that all axes and angles are moved, but the system remains the same. The system, it means like we had hexagonal symmetry, it's still hexagonal symmetry, but with another ABC and angles. We can change A, B, or C. So we can this parameter do free. It allows us to make a lot of things. We can change everything. We can change everything but keep the symmetry. We can change only A, B, or C vectors. We can change only the X component of axis. It means X component. It means that I can change only these components, for example, not AB, but I can change, for example, only this component. So it's a lot of possibilities. And for our 2D case, only X and Y components are allowed to change. That it is not allowed to change because in this way we'll get the same graphite. From graphene we'll get the graphite in a lot of time. It really will take crazy time. And another interesting thing here, key points. You see, here I used 8. Can somebody explain why I use so different key points? So why here is 4 and here is 1? How do you think? And here is 8. Yeah. It's surface, yes, but
we don't need to calculate more points since
yeah, it's the first. What means that points? It means that X and Y points. It means that here we have two vectors, B1 and B2. It means that in this B1, we take, for example, 8 key points. It will be 1, 2, 3, 4. So it will divide this vector into 9 slices. 8 key points, it will divide it into 9 slices. B is the same. Vector B is the same. It will also divide it into 9 slices. But then Z, in that direction, we need nothing. We are staying in some gamma point, and we used only one key point to have some energy in this direction. But we don't fill this. We don't fill this space with key points. That means that we have only one layer. We have only one layer by using by using this key point 1. And why we use here 8 key points and here we use 4 key points for graphite? Because vector A in graphite, it's almost 2 times smaller than vector C in graphite. That's why in reciprocal space, this direction will be 2 times higher, and this will be 2 times lower. What does it mean? What does it mean? It means that, you see, this vector, it's a few times smaller than this vector. Yeah, 3 times. 3 times because I took the CIF file. And no, maybe 2 times. I don't know exactly. Yeah, it's almost okay. 2.7, something like this. This thing is 2.7 times smaller than this C. That means that in reciprocal space, this vector should be 2.7 times bigger than this. And we see this is not so huge as this direction. That's why we need a lower amount of key points to make to calculate this energy in this direction. 2 times, almost 2 times, like 2.7. I took 2 times. But for graphene, I need only 1 key point because I don't want to go bulk. I don't want to go bulk. I just want to stay in this 2D. And there is nothing to calculate here. It's just vacuum. Okay. And yeah, I think it was all the differences. Then we have self-consistent files we should place here. So CMDM,
from this calculation, from this relaxation. And okay, well, okay, let's make relaxation, and then we move to another parts. You have that lab 5 archive. In this archive, you have these three folders, and we are starting with Relax. This file is in Relax. And I open it in terminal. I think maybe you have done it. Yeah, if you take some, yesterday I tried it and it was like 3 minutes. Maybe now it will take more time because my computer also has Zoom and this projector. Here is our output. For bulk material, last time that we have created graphite, we saw that output, it was like sodium-1, sodium-3 last data. You see, we have here this kilobar, so we have almost 0 pressure on the, we have 0 forces, so we have made all correctly. Fermi energy, but we don't need it now. This is the last SCF calculation, and we should go before this last SCF calculation to find the parameters for this calculation. So it took these parameters. Here, it took this parameter and final coordinates. So begin final coordinates. Here are our output. Here we don't have this sodium-1 and sodium-3 separated, but we have this matrix for cell parameters. A lot. It means a atom of sodium-1, which we typed. So we have started from this parameter. We have started from 4.65. Then it changed the matrix. This matrix of parameters. You can calculate what is 4.65 multiplied by that thing. It should be where is it? It should be like this. 4.62. It was 0.65. Now it's 0.62. All the things are important. So if we are doing some good calculations for some research, we should get so difference in 0.3 Bohrs. It can be very important. But this 10, it stays 10. Because why we don't we can do it before. I will show you some output from lab 4 from previous lab. Here is relaxation. We see relax. It's for graphite. For graphite, it's like 3D material, and I will show you here final coordinates. We also can do it. We also had this 4.65. We can multiply, but for and here is sodium-3. You see 2.67. But here we had this useful thing here. Sodium-1, but for 2D we don't have them. I don't know why. I don't know why, but guys who created this output format, they didn't include it for 2-dimensional crystals. So if you will multiply 4.65 on the thing, you'll get the same. You will get this. So that's the point. We can do it every time. Okay, we can start SCF calculations. We just take that, yes, and move it to SCF because it's our new coordinate for SCF. And then we can start this SCF's calculation. It should be very fast, even on my busy computer. Yeah, the point of relaxation is to get structure. The most useful information we can get from relaxation step is a structure. Structure without pressure. I saw some meme like there was graphite wife and graphite children, and father diamond, and the mother told that your father was under high pressure for a lot of time. Here we got this out file for this graphene, and what information should I get from here? I should get this Fermi level from SCF out. And then next step, you take all these files, copy them into band folder, and it will be used, this output will be used in band structure calculation. Yeah, and also you had to put this number into band input file. See, you take output of SCF calculation to band structure, to band folder, because band calculation is non-SCF calculation, non-self-consistent, and it. Yeah, you should also place this lattice parameter in the input, this band in, and will we placed it in SCF calculation. It's band. It's another file. No, we had we made SCF. Yeah, you should copy all files from SCF folder to bands folder. Graphene bands. This band calculation, it needs output of SCF calculation to be proceed. Everything works. Yeah, it's magic. And okay, I will launch it and then show you the difference. The difference to graphite. Yeah, bend in to bend out. Not yet. And I want to show you, now you will launch this calculation, and I want to show you the difference between these two. The difference between these two files, for graphene and for graphite. Yeah, the difference is rather simple. You have another structure. This is a stan, and here relax at 2.79, 669. Key points. Yeah, we don't have for graphite we have 8 key points. For graphene we have 4 key points. You see, this for gamma, MK gamma, without this thing. Why? Because ALHA it's some bulk stuff. It was imported for bulk, but here we don't have any bulk. You see the for graphite, yeah. For graphite, our path was like gamma M K gamma, yeah, and then we moved to the border of this brilliant zone to A, and then we have A, L, H, A. But for graphene, graphene, we don't have this thing. We don't have this stuff. We have only one, and that's why we have a lower amount of these key points. Here we N, B, and D. It was 16. We should type 8, so it's also twice lower. What is NBND? A number of bands. It depends on 8 on valence electrons. For C, for carbon, we have 4 valence electrons. So if in graphite it's 4 atoms inside unit cell, we should type 16 NBND. Here we have only 2 atoms. 2 multiplied by 4, it's 8. We have 8 NBND, and that's all. So we can make post-processing. We can it makes file bands X, graphene band 2, out. Here is post-processing. It also will take some seconds. Post-processing. What we can get from here, from post-processing? We can get these coordinates. These coordinates of our high symmetry points, and we have this file graphene band that, and we have to graphene band that GNU. It's even more convenient. We had to plot it. I don't remember if I placed Fermi energy. So you had placed here Fermi energy from SCF in this graphene plot PI. I hope you are. I hope now you are quite familiar with this script. You all got this. Okay, let's discuss in few words this file, this plot. First of all, you see this Dirac point in key point, as I promised. So we had this calculation, this tight binding model, and we choose key point as this high symmetry point as some interesting point, because when we calculate energy dispersion at this point, we'll have linear dispersion, and the linear dispersion will be like this. And this is one method, tight binding model, and DFT is just another method, more advanced, and we get the same linear dispersion. And just for to see how it is cool, you see it's really linear. Of course, it has. If I will close very close, you see it slightly misleaded on this line on Fermi energy, but it means that we didn't take enough accuracy, we didn't take good potential. We just used LDA functional for this, but we had to use some slightly more advanced functionals. But it's also okay. This difference is not huge, and you see this these bands, they not cross they not interchange, because if I will make it a small gap, a tiny thing, yeah. Okay, I want to change to it. And also, I have showed you this very simple model from Hoffman book. You remember this thing, yeah? I showed you how to take this 2D band structures, and we took just this simple parabola model and made this thing. And you can gamma xm gamma in this thing. You see gamma x xm, and now we can see the same thing in for graphene. For graphene, from gamma to m, it's almost parabola. From m to k, almost parabola. From k to gamma, it's almost parabola. So it's our primitive model with this infinite chains of atoms. It was rather okay, because even for these carbon atoms are rather simple. We can in some way say that yes, these atoms are localized near them. This line, this band stands for s orbital, and s electrons, they are very close to carbon atoms, to carbon nuclei. That's why we have near parabola model. Not quite important. So importance of this point, it means that it is close. It's located on the Fermi level. It means that this 0 Kelvin, we have all electrons sitting here on this orbitals. But when temperature slightly changes, some electrons goes here on this band. And that's why they are very fast. It means it gets this semi-metal behavior of graphene, of graphite, of graphene. So this is very interesting, because slightly changes in temperature, it means that we have a lot of these electrons, a lot of this. We have a lot of this relativistic electrons. But here so this is S, this is P, and nothing quite changes here. It's not so important. Okay, it's all for today.